A very good morning to one and all. Welcome to day 2 of a 1-week faculty development program on advanced materials processing and characterization methods. I am very happy to introduce today's eminent speaker, Dr. Prabhakaran Tandapani sir. Dr. Prabhakaran Tandapani, currently working as an assistant professor, senior grade 2 in the Department of Physics at the School of Advanced Sciences, Velu Institute of Technology, AP University, Amaravathi, earned his PhD in physics from the National Institute of Technology, Tiruchirappalli, India. His research focused on magnetoelectric polymer nano-composite films. Subsequently, he held positions as an assistant professor at NITT and Central University of Tamil Nadu, India, for 2 years. During his tenure at CUTN, he was awarded a Fondesit Postdoctoral Award by the Government of Chile, enabling him to conduct research at the University of Concepcion, Chile, from 2015 to 2018. Following this, he pursued a postdoctoral fellowship in a project funded by FAPESP, Sao Paulo, Brazil, under the postdoctoral contest 2018 in Brazil from March 2019 to April 2021. Dr. Prabhakaran specializes in condensed matter physics with a focus on developing magnetic nanomaterials and multifunctional nanocomposites using chemical methods for applications in sensors, energy, and biomedicine. His research interests span magnetic nanoparticles, intermetallic alloys, nanovites, multiferroic materials, ferroelectric polymers, nanocomposites, magnetocaloric materials for refrigeration, and magnetic nanoparticles for magnetic hyperthermia in cancer treatment. He has authorized 25 journal publications, 31 conference proceedings, and 4 book chapters, accumulating a total of 829 citations with an H index of 14 and an I-10 index of 17. Additionally, he has delivered invited talks at various institutes. Dr. Prabhakaran has been recognized with several awards, including the Young Researcher Award 2011 in NIT Calicut, India, for the best paper presentation. The SPIE Officer Travel Grant 2011 from SPIE USA, and he served as the president of the NITT SPIE student chapter in 2011. He also received an international travel grant from SEB India to present a paper at ICMAT 2023 Singapore. Now, I hand over the session to Dr. Prabhakar sir. Sir, hearty welcome, sir. Please carry on, sir.
Yeah, very good afternoon, everyone, and thank you for your nice introduction. And now I'm going to share. Okay. Can you see my presentation?
Yes, sir.
Okay. Okay. Once again, very good afternoon, everyone. And first of all, I thank the organization for inviting me for this FDP, online FDP for 1 week. I am mainly focused on the magnetic materials, and today I'm going to talk about magnetic materials and composites for different applications. I will initially start with basic introduction to nanomaterials, magnetism, and what is functional materials. Then we will focus on magnetoelectric nanocomposites for sensor applications, and then we will move on to magnetic refrigeration, whereas ferrites, graphene-ferrites, as well as single crystals have been focused in this talk. Okay. So let's start with this diagram, and what you see is the dimension of the materials And based on the dimension of the materials, we classify the materials into different categories. And whereas we mainly focus on nanostructures, the material which falls within 1 to 100 nanometers are known as nanostructures. And you can able to develop these nanostructures by bottom-up approach and top-down approach. The basic methods how to achieve structures. And when we use the size scale of composition from bulk to nano size, they exhibit an excellent properties than the bulk one. And they have a better surface area, we say, due to that it has a high catalytic property, and you can use these nanostructures for antibacterial properties, and hardness of the material is better than the bulk. The electron energy band gap can be engineered, and the electrical properties and magnetic properties can also be fine-tuned when we reduce the size of the bulk material of the same composition to nanostructures. Okay, here we are mainly focusing on.
Sir.
Yes.
So slides is not changes, sir.
Slide. No.
No, sir.
Okay.
Now it's okay, sir.
Let me share it again. Can you see?
Please
is it changing now?
Please change slides, sir.
Yeah, I'm changing it. So now I'm in fourth slide. Can you see?
Third slide will be visible, sir. Introduction.
The fourth one?
Not changed, sir. Now it's okay, sir.
So in this mode, is it fine or is it changing now?
Change it, sir. Now it's okay, sir.
So is it changing now?
Now it will be changed, sir. Now present in fourth slide, sir.
Okay, now can you see the type of magnetism here?
Okay, sir.
Oh, can you see the slide? Fifth one?
No, sir. Fourth one.
Okay. 1 minute. Give me a minute. I will stop sharing and then I will. Sorry for this glitch. Okay. Now you can see the entire screen, right?
Yes, sir. We are seeing, sir.
Okay. Is it moving now? Can you see?
Yes, sir. It is moving, sir. Yes, sir.
Okay. Sorry for the disturbance. It always happening in online when we have this. Okay, fine. So here we mainly focus on magnetic materials for different applications. And you might be knowing different types of magnetic materials. We say they are ferrimagnetic as well as superparamagnetic and antiferromagnetic materials. Based on their dipole alignments, we say they are classified into different categories. And especially we need to check their magnetic susceptibility, right? And based on their value, we classify the material into these 4 different categories. You know how this, in the case of paramagnetic material, the magnetic dipoles are randomly aligned and it does not have any net magnetic moment in the absence of magnetic field. In the case of ferromagnetic material, the magnetic dipoles will align along the field direction, right? Even in the absence of magnetic fields, and it has some spontaneous magnetization. Okay, so the net magnetic moment will be here in ferromagnetic material. But in the case of antiferromagnetic material, though the magnetic dipoles have the same magnitude, but they are anti-parallelly aligned. That leads to a zero net magnetic moment in the absence of magnetic field. But in ferrimagnetic material, they have some magnetic moment because the magnitude of the dipoles are not let me check this one. Okay. This not equal, so there will be some net magnetic moment. Okay. And here, based on the magnetic hysteresis loop, we classify the magnetic material into soft and hard magnetic materials. And we have the applications depending on how much hysteresis loop area the material has. Based on that, we will use the material for recording media and various applications. Okay. And here, the magnetic nanoparticles show a particle size dependent property. And if you look at in this diagram, when the size is reduced from a bulk to a nanoscale, it shows a multi-domain in a bulk material. And then when we reduce the size to a critical size, it has transformed into a single domain. You can see what is multi-domain and single domain here. In multi-domain, we have many number of domains, and whereas the dipoles will be aligned in one particular direction. But in the case of single domain, we will be having only one domain. Okay, and whereas you can able to easily flip the magnetic dipoles in a particular direction. And here in the case of superparamagnetic material, it does not have any hysteresis. Okay, so that there will be a zero remanence and zero coercivity. And we say these type of nanoparticles with an uniaxial anisotropy randomly flip the direction of their magnetization. Okay, we say this effect is induced by thermal energy, and the average time to require to perform this flip is known as relaxation time. And when we compare this relaxation time with the measuring time, tau m, if the measuring time is much less than the relaxation time, it will transform into a blocked state, or else we say ferromagnetic state. If the measuring time is much greater than the relaxation time, it will show as superparamagnetic because the thermal energy will be higher at this relaxation time, or else we say at room temperature. Okay, and to check their transition, we say it transforms from the superpara to a blocked state or a ferromagnetic state. We need to perform a field cool curve or zero field curve. And here, what you see in blue is zero field curve. Okay, and this one is field cooling curve. And this must be done at a lower field of 100 wire step. And depending on the field, you may have the transition at different temperature also. But generally, we do this analysis at 100 wire step. When we do this and the material transform at this particular temperature, and above, let's say 120 Kelvin, it behaves superparamagnetism. But below 120 Kelvin, it shows a ferromagnetic nature. Okay, and then we mainly focus on spinel ferrites. It has a general formula of AB2O4, whereas A2 is a divalent cation and B3 is trivalent cation. It has spinel and inverse spinel structure. Based on the arrangement of divalent and trivalent cation in A and B sublattices, we classify the spinel ferrites into normal spinel and inverse spinel structure. And these spinel ferrites has features like good chemical stability, low electrical losses, high electrical resistivity, and it has high room temperature coercivity and moderate saturation magnetization value. You can able to synthesize these spinel ferrites by physical and chemical methods of any form, let's say in nanoparticles or nanostructures. You can synthesize in the form of thin film nanocomposites as well as coaxial nanostructures. And depending on their saturation, magnetization, coercivity, or we say based on their hysteresis loop behavior, we use these spinel ferrites and magnetic materials for different applications. Even you can check here in the small toys, we use a magnet. In magnetic recording media and biomedical applications, we use the magnetic nanoparticles for treating a cancer cells. We use magnetic materials to be an refrigerant in refrigerators. We can use the magnetic nanoparticles as a carrier to treat the cancer cells. In addition, you can see on the other side, we use it in mobile and lifting machines, transformers, motors, right? We use magnetic materials in a wide range of applications. And let's move on to the functional materials. What do you mean by functional materials? The materials which exhibit more than one properties that can be significantly controlled by external stimuli simultaneously is known as functional materials. There are different external stimuli. We say magnetic field, electric field, temperature, and mechanical field can be considered as external stimuli. Here, we can combine any two properties, let's say optical and magnetic properties. I can able to fine tune their optical property by using a magnetic field. Okay, in the same way, by applying some light energy, if I can able to fine tune their magnetic properties, and there is some functionality, right? The same material has better optical as well as magnetic properties. Similarly, electrical and magnetic properties can also be merged, or we can fine tune their magnetic property by electric field or electrical property by magnetic field. So some examples are given here. Thermal magnetic properties, magnetic and structural properties can be combined. Similarly, mechanical and thermal properties can also be done. And it can be realized in certain single-phase materials and also in composites. These combinations can be done in single-phase materials as well as in composites. Okay. In this talk, I'm going to focus on these two parts. One is on multiferrites, the another one is in magnetic refrigeration for cooling application. Let's start with multiferrites. So what do you mean by multiferrite materials? I said what is functional materials is, right? Now we are going to see what is multiferrite materials is. Okay, the multiferrite materials exhibit more than one ferrite property simultaneously. It exhibits more than one primary ferrite orders property simultaneously. So here we have the primary ferrite orders are ferroelectricity, ferromagnetism, and ferroelasticity. If you consider them individually, let's say ferroelectric materials. In the case of ferroelectric materials, we say P as polarization, electrical polarization. This electrical polarization we can able to fine tune by their electrical field B. In the case of ferromagnetic material, the magnetization can be controlled by an external magnetic field H. Similarly, in the case of ferroelasticity, we need to apply some stress so that we can change their strain. Okay. Here, when we consider these three ferrite orders separately, the ferroelectric materials, they have spontaneous polarization, ferromagnetic material, they have spontaneous magnetization, ferroelasticity materials, they have spontaneous strain. But when we combine these two materials, let's say ferroelectric and ferromagnetism, what is the beauty of this material? One is, initially we say in ferroelectric material, we can fine tune their electrical polarization B by an external electric field. Magnetization by external magnetic field H. But when we combine these two, ferroelectric and ferromagnetism, we can able to fine tune their electrical polarization by external magnetic field itself. And the vice versa is also possible. The magnetization can be controlled by an external electric field, right? We say this functionality as magnetoelectric effect, right? Due to this functionality, we have various applications of this material. If we can combine this ferroelectricity and ferromagnetism in a single material, if we can fine tune their electrical polarization by an external magnetic field, we can use that material for various applications. But achieving this magnetoelectric effect at room temperature is a challenging task. Okay, because the mechanism favoring ferroelectricity and ferromagnetism contradict each other. For ferromagnetism, say the d orbital should be partially empty, but in the case of ferroelectric material, d orbital should be completely empty. Okay, that is, we say that competition between ferroelectricity and ferromagnetism, they contradict each other. Okay, and there are some materials have been found with magnetoelectric effect. With ceramic materials and composites, you can see the list here, but they have the drawbacks. They exhibit either weak ferroelectricity or ferromagnetism in room temperature. They are brittle and has high leakage current density. In order to overcome these drawbacks, we came up with an idea to achieve a polymer-based magnetoelectric nanocomposite films. Here, how we can able to synthesize this polymer nanocomposite, we need to add a ceramic materials in the polymers. To give a simple example, you can consider the concrete. Okay, in the case of concrete, we use cement as a matrix, granules, rods, or reinforcement to achieve a strong beam, right? Strong beam or pillar. This is a simple example for the composite, whereas we have cement as a matrix and then granules, sand, and rods or reinforcement. Okay, in the case of polymer nanocomposites, we use polymer as a matrix, which is acting as a binder, right? And magnetic nanoparticles or the nanoparticles are known as a reinforcement. So when we mix these two, when we fabricate with the help of these two, then we can achieve polymer nanocomposite. What is the advantage of polymer nanocomposites? They are flexible. That is a major advantage. Lightweight and high mechanical strength. You can mold the polymers into any shape, complex shapes, and less production cost. These are all the advantages of polymer nanocomposites. I said we are interested to fabricate magnetoelectric polymer nanocomposites. Okay, the first aim is to achieve a freestanding flexible polymer-based magnetoelectric nanocomposite films. How can we do? We need two ferrite orders. One is ferroelectric ordering and ferromagnetic ordering. Then only we say magnetoelectric polymer nanocomposite. Right. In this case, we have chosen the following materials to achieve magnetoelectric polymer nanocomposites. One is ferroelectric matrix and magnetic nanoparticles as reinforcement. Which polymer can be chosen for ferroelectric? Polyvinylidene fluoride can be chosen as a ferroelectric matrix. And various ferrite nanoparticles are available. Here we have chosen, let's say, nickel ferrite, cobalt ferrite, zinc ferrite, and magnetite as reinforcement. So what happened when we combine these PVDF and ferrite nanoparticles? We anticipate that, right? The synergetic interaction between the PVDF and ferrite nanofilters would give rise to extra degrees of freedom for the magnetoelectric effect, right? Then we can say there is magnetoelectric effect at room temperature. This is our idea. And I told you we have chosen PVDF, right? The PVDF has a monomer unit of CH2CF2, and it has different crystalline polymers. We say alpha, beta, gamma, and gel. You can see the structure of the different crystalline polymers, beta, alpha, and gamma. In the case of beta, it has trans gauges, but in alpha phase, it has trans gauge. But in gamma phase, it has trans gauge, trans gauge, like that. Okay. And among all crystalline polymers, beta phase of polyvinylidene fluoride is much attracted because it has an inbuilt electrical dipole moment. When it has inbuilt electrical dipole moment, it can have some ferroelectric polarization. We say spontaneous polarization as well as piezoelectricity. That's why we have chosen PVDF as a matrix for this investigation. So how can we synthesize this composite? You can synthesize the composite by solvent casting method. We need magnetic nanoparticles for magnetic ordering. The magnetic nanoparticles can be synthesized through a combustion method that we have adopted. We use DL-alanine as a fuel, and which is an excellent fuel to achieve a single phase nanoferrites. You don't have to do the calcination at higher temperature. Even as prepared, the nanoparticles is found as single phase. Okay, that is the beauty of this DL-alanine fuel. And here you can see different ferrite nanoparticles synthesized through the same method, and they are available at different sizes. The PVDF is found to be flexible and freestanding. The thickness of the PVDF is around 90 to 100 micrometer. And the same analysis show that it has a spherulite. We say this as spherulite structure as well as lamellar structure. The tree branches like thing, we say lamellar structure, which confirms This fabricated film has both spherulite. Spherulite corresponds to beta phase. This lamellar structure is correspond to alpha phase. So it has two phases, alpha and beta phases. And we have made the solution casting, we have used solution casting method to synthesize the composites of different combinations. Here we use three different ferrite nanoparticles of different weight fractions. Let's say from 0 to 28% we have chosen to study the effect of filler on their ferroelectric and ferromagnetic property, as well as the magnetoelectric cross coupling. You can see the white spots are not there, right? The okay. Right, and you can see all these compositions are flexible in nature and no need of support. That's why we call these composites as freestanding flexible nanocomposites. Okay, and we are saying through the SIM that it has beta and alpha phases. We can further quantify or confirm through FTR analysis. We know Fourier transform infrared spectroscopy. With this spectroscopic technique, we can quantify the fraction of beta phase in the composites. Okay, here we have the pristine PVDF and the composites synthesized with cobalt ferrite, PVDF cobalt ferrite of different weight percentages. The beta and alpha phases are marked in the spectrum. Okay, how to quantify the beta phase from this? We have to apply the VIT-Lambert's law, right? And here the equation has been proposed by Gregorio. With the help of this equation, we can able to quantify the beta phase. Here in this equation, we have A alpha, A beta are absorbance at 766 and 840 per centimeter. They correspond to alpha and beta phases of PVDF respectively. And the constants K alpha and K beta also you can find here. And this is nothing but absorption coefficient. Okay. The A alpha, K alpha and K beta are absorption coefficients that is determined based on the crystallinity and all. Okay. And how the beta phase is varies in the composites. We can see here. We have given the concentration versus fraction of beta phase on the y-axis, right? Of the different composition, you look at it, the maximum fraction of beta phase achieved at different weight percentages. It is not uniform in all the cases. If you look at PVDF cobalt ferrite, if you ignore the plain PVDF, the beta phase has been enhanced at 5-8%, but at higher fractions, it's not supporting the enhancement of beta phase. In the case of PVDF nickel ferrite, at 10-8% shows better. In the case of PVDF zinc ferrite, 15% of zinc ferrite shows better fraction of beta phase when compared to other composition. It means that the nature of ferrite, right, the type of magnetic ferrite that we have chosen plays an important role in enhancing the beta phase of PVDF. Okay. Now we have quantified the beta phase, right? We have synthesized magnetoelectric nanocomposites, but before we call these composites as magnetoelectric, we need to prove whether they have ferroelectric and ferromagnetic nature. Do they have a cross coupling between ferroelectricity and ferromagnetism? Then only you can call these composites as magnetoelectric nanocomposites. Okay, how to prove this? We can prove that through analyzing the magnetic hysteresis and ferroelectric hysteresis loop at room temperature. In addition, we should also prove their cross coupling between them. So how can we do? We have to perform their ferroelectric property at different DC magnetic field, right? That will give an evidence for cross coupling. The first thing, we have proved their magnetic order at room temperature. What you see here is cobalt ferrite and the corresponding MH loop. On the other side, we have PVDF cobalt ferrite. Okay, the next composition, we have nickel ferrite and PVDF nickel ferrite. So what you observe here, whatever the nature we have in nanoparticles is reflected in composite as well. But the magnetization will not be equal to the ferrite nanoparticles because the PVDF is non-magnetic. But one thing you have to remember, we convert a non-magnetic PVDF into a magnetic composite, right? But the nature is very similar to the nanoparticles that we have chosen here, right? And here what happened when we increase the ferrite content in the PVDF matrix, the magnetization will definitely increase because it depends on the ferrite content, okay? Now, we have proved their magnetic nature. Magnetic ordering is proved. Now, we need to prove their cross coupling. Let us assume we have proved their ferroelectric property at room temperature. We have done it. And to prove the cross coupling between the ferroelectricity and ferromagnetism, we have used this setup. In this setup, you can see the PE loop tracer and DC magnetic field and the power source. Okay, we need to place the sample in the magnetic field. Okay, so at constant magnetic field, we will study the electrical polarization. Okay, so what we have done this analysis at different magnetic fields, say from 0 to 4 kilovolt. Okay, and what you see here, the ferroelectric polarization is declines with increase of magnetic field, right? The magnetic polarization declines with increase of magnetic field, and then it's saturate or remains the same at higher magnetic field. Let's say at above 2 kilovolt state, it remains the same. And what is happening on other composites? In PVDF nickel ferrite, we have observed the electrical polarization increases and then saturate at above 1 kilovolt state, or we can say at above 2 kilovolt state remains the same. There is no much variation. Why there is no much variation at about 2 kilovolt state and 1 kilovolt state in the case of cobalt ferrite and nickel ferrite? Because we say the magnetoelectric effect in these composites is the product property of piezoelectric effect and magnetostriction. So I can say there is a magnetostriction and piezoelectric effect. Here in the composite, we have two components. One is piezoelectric matrix and magnetic nanoparticles as a reinforcement. When we subject these nanocomposites in the DC magnetic field, the magnetic nanoparticles will experience magnetostriction. Know what is magnetostriction in practice, right? When the magnetic material is subject to a magnetic field, its dimension may change. It may elongate or it may contract based on their magnetostriction coefficient. It may have positive or negative value. So the magnetic nanoparticle present in the polymer matrix will experience magnetostriction effect, right? Which means that the dimension changes, right? That will induce strain over the piezoelectric matrix. Which one is the piezoelectric matrix here? PVD, right? When the pressure is applied to the piezoelectric matrix, it will generate some electrical charges, right? That's why we see change in electrical polarization here when we increase the magnetic field. But after certain magnetic field, it does not induce any electrical, it does not change the piezoelectric effect, which means that it reaches its saturation limit. The magnetostriction effect reaches its saturation limit. That's why there is no much variation after 2 kilovolt step. Okay, and here in these two compositions, the magnetostriction coefficient of these two are given here. You can see the cobalt ferrite has positive 130 and nickel ferrite which has minus 24.5. That's why we say decreasing and increasing trend in the case of PVD, cobalt ferrite and nickel ferrite respectively. Okay, and where do we use these magnetoelectric nanocomposites? We can use these magnetoelectric polymer nanocomposites for energy harvesting application. Here, as an example, you see, we say that the magnetic field is applied to this magnetostriction material, right? That magnetostriction will induce a strain over the piezoelectric material, and we say that is magnetoelectric effect, right? Here, when the magnetic field is applied to these composites, the magnetostrictive phase will deform. That deformation is transmitted to the piezoelectric phase, right? And then there will be an electrical charges. And here, as an example, you can see Tefenol D, PZT Tefenol D laminate composites have been fabricated, which can able to produce an energy density of 2 milliwatt per cubic inch with a vibrations of 21 hertz and 100 milligram. Okay, we can use these composites for wearable energy harvesting systems. Like you can put it inside the sole of the shoe, right? Then you can use it to charge a battery. A small battery can be charged. And then you can use the same material for field sensors. We say magnetic field sensors, right? So this deformation directly leads to a polarization. Okay, this deformation will directly lead to a polarization. And these magnetic polymer nanocomposites can be used as a self-powered magnetic field sensors that directly transfer magnetic energy into electrical signals. Okay. So to summarize the first part of my talk, we have seen the ferroelectric and ferromagnetic property at room temperature and cross-coupling between ferroelectricity and ferromagnetism on these composites, right? And what we have understood, the ferroelectric phase, we say beta phase of PVDF, ferrite type, and ferrite content, magnetostriction coefficient are important parameters to achieve better magnetoelectric effect at room temperature. Okay. Now we move on to the second part of my talk, whereas I'm going to focus on magnetic refrigeration. Right. We know this, right? I hope you all familiar with this picture. We say this is smart card, right? Our grandparents, you can consider in 80s, even more than 17th century, they use mud pots to store water. Even here, the summer has started. If you want to enjoy the cold water, our grandparents uses these pots, right? But they failure to store food, vegetables for a week or for a longer time. But after the Industrial Revolution, we came up with a device known as refrigerator. Since then, we started using this refrigerator for various applications, not only store food, not only store water. We use it for various applications in medicine, in supermarket, in labs to store chemicals, and some organs, right? We started using the refrigerator for various applications. Okay. Even here, I have given the classroom picture because the refrigerator and air conditioner, they work based on the same principle. Okay. And we started using almost in all automobile industry, we have the AC. How this refrigerator works, they works based on vapor compression and expansion cycle. We have the internal heat exchange coil, and here we have external heat exchange coil. The important components of the conventional refrigerator, what we have it at home, is having an electrical powered compressor and then expansion valve. Okay, and this internal heat exchange coil will be put it inside the refrigerator, and the red one will be outside the refrigerator. You may have seen some coil or jacket backside the refrigerator. If you go back to home, and then you can take a look. But once we switched on the refrigerator, we don't care about it, right? It will work 24/7, isn't it? What happening there? There is some refrigerant, right, in the form of gas. The refrigerant will pass through this compressor, right? Then it will eject a hard compressed gas through the outer jacket, and then hard compressed gas, the heat will be ejected to the environment, and then through the expansion valve. When the hard gas is passed through the expansion valve, due to the pressure variation, it will cools down, right? Then we will be having a vapor here, cold vapor. When the cold vapor is passing through this inner jacket, it will absorb the heat from the environment and then condense, and it will again pull into the compressor. Okay, this is the cycle we have. The gases that we use here is toxic to the environment. We know the major refrigerants in conventional refrigerators are chlorofluorocarbon, hydrofluorocarbon, right? Methane, ammonia, right? They are used as a refrigerant. Almost in domestic level, we have replaced with green refrigerants, we say R34. But in large-scale industrial applications, we still depends on the fossil fuels. Okay, and it creates some environmental impacts. It emits a carbon dioxide to the environment. You can see from this diagram the ppm level. It has reached only up to 400 ppm in the year 2017, but by this time it reaches about 450 or 500 ppm. Okay, it looks like a very low concentration of carbon dioxide in the environment globally. But look at this temperature anomaly graph. The temperature anomaly that we have seen throughout the year is about 0.8 degrees Celsius, right? And this is the reason we have a global warming. The carbon dioxide emission to the environment leads to a ozone depletion, right? And then we have a temperature anomaly, temperature rise, and global warming. What is the cause? We have various causes: deforestation, industrialization, burning of fossil fuels, pollution of automobile, thermal power plant, air conditioners, and refrigerators. Okay, among all of these causes, air conditioners and refrigerators is also one of the cause for the global warming, where we are going to mainly focus on magnetic materials which will replace the fossil fuels. Okay, first we should understand what is magnetocaloric effect is. The magnetic materials that exhibit remarkable change in their temperature when they are adiabatically magnetized and demagnetized. We say this as magnetocaloric effect. To use a magnetic material for a refrigeration application, the material should exhibit better magnetic entropy. We say delta S or entropy change, adiabatic temperature change delta T, within a moderate field of 1.5 Tesla, or it should be less than 2 Tesla. Okay. And then refrigerant capacity should also be higher. So what is happening when the magnetic material is subjected to a demagnetization and magnetization in an adiabatic condition? The entropy will change. The entropy of the system will change. The entropy is obtained through the coupling of magnetic spin systems with the field, magnetic field under adiabatic condition. We say the entropy of the system is the sum of these three components, Sm, Sl, Se. And here, the magnetic entropy of the system is a function of temperature and field, but the lattice entropy and the electronic entropy are independent of magnetic field. What does it mean? When the magnetic material placed in an external magnetic field, the magnetic entropy will change, and others will not change, remains the same. But according to the law of conservation, the entropy of the system must be the same, right? So, in order to overcome the change in entropy, the lattice and the electronic entropy will also change. That leads to heat in temperature, right? That leads to heat the magnetic material. So, we are going to see that here. How does the magnetic refrigerator works? We have to consider a magnetic material at room temperature. Let's say the dipoles are randomly aligned. Okay, when we magnetize adiabatically, what happened? The dipoles are aligned along the field direction, and the temperature now is above the reference temperature Tr. If we remove this temperature, the excess temperature isothermally with a heat sink, we can bring down the temperature equal to the reference temperature Tr. Now, if we demagnetize the material adiabatically, the temperature will be lower than the reference temperature, whereas it's capable of absorbing the heat from the external agency isothermally, and then it reaches the thermal equilibrium, let's say Tr. This is one cycle, how the magnetic refrigerator works. Okay. I hope you got that point. What is the difference between magnetic refrigerator and conventional refrigerator? Where there is a difference. Look at this diagram. In the case of conventional refrigerator, we have the compressor and the expansion valve. These components are very important, one for the function of conventional refrigerator, but we have not use this compressor or expansion valve in magnetic refrigerator, because this compressor and expansion valve will consume a lot of energy, and it may create a noise also. But in the case of magnetic refrigerator, we use magnetocaloric materials as refrigerant, which is a solid materials which do not emit any toxic gases to the environment. But to magnetize and demagnetize, we need an external magnetic field, which is around 2 Tesla, or which is less than 2 Tesla. Okay. And then we need hot and cold heat exchangers. Okay. And if you compare the efficiency of this magnetic refrigerator with the conventional one, we can able to achieve nearly of 60% of efficiency than the conventional refrigerator. How can we quantify this magnetocaloric effect? We have two methods. One is direct and indirect methods. We need to quantify adiabatic temperature change, magnetic entropy change, and refrigerant capacity. These are all the important parameters we need to quantify through these two methods. Okay. The isothermal magnetic entropy change can be estimated by using Maxwell equation, and adiabatic temperature change can also be estimated, but we should know what is the specific heat capacity of the material and magnetization value. If we know, we could estimate the adiabatic temperature change. And here, the magnetic entropy change may be positive or negative. We call that as normal and inverse magnetocaloric effect, respectively, right? And then the last parameter, the refrigerant capacity, can be estimated by using this relation. This will give you how much heat has been exchanged between the hot and cold sinks per a minute or per a cycle. And this three parameters should be quantified to say whether the material is useful for refrigeration or not. Okay. Now, we say magnetocaloric effect, right? There is a change in magnetization. This change in magnetization should be achieved close to the working temperature, or say it should be close to the room temperature, okay, depending on the application. The magnetocaloric materials are classified into two categories. One is second order phase transition material, in short we say SOPT, or in which the ferromagnetic material, antiferromagnetic material, and ferromagnetic material will transform at Curie temperature, Neal temperature, and blocking temperature, respectively, right? And the ferromagnetic material will transform into paramagnetic. When it will transform into paramagnetic at Curie temperature, antiferromagnetic at Neal temperature, and superparamagnetic material, right, at blocking temperature. So we will see these transition. There is only a magnetic transition in the case of second order phase transition material. In first order phase transition material, they have both. We say magnetostructural transition. There will be a magnetic transition as well as a structural transition at a temperature. We say at a critical temperature, there is a magnetostructural transition. Okay, and here these magnetostructural transition materials, or else first order phase transition materials, found better magnetocaloric effect when compared to the second order phase transition materials, but they exhibit thermal hysteresis. The thermal hysteresis are not allowed for the refrigeration application, whereas the second order phase transition material does not show any hysteresis loop, but the magnetic entropy change is comparably less than that of first order phase transition material. There are various materials have been obtained so far, whereas FeRH and gadolinium based composites have been found to be a better magnetic refrigerant so far. And gadolinium based material have already been proposed as a prototype magnetic refrigerator by GE Electricals. And if you look at the publications, say the number of publications increases every year. And this has been done based on the keyword magnetic refrigeration. And we mainly focus on ferrite as a refrigerant for cooling. And why we have chosen this ferrite as a refrigerant? We have seen previously that the ferrite shows particle size dependent magnetic properties. We can control their size so that we can bring down from multi-domain to a single domain size. If we bring down from multi-domain to single domain, it will exhibit a superparamagnetic nature. Right. When the material has a superparamagnetic nature with sufficiently high magnetic moment, we can use these nanoferrites as refrigerant or cooling. Okay, and here if we fine tune their composition, we can increase or decrease their working temperature or blocking temperature close to room temperature. It has a low global warming potential, non-toxic, inflammable, low production cost and durability are the advantages of these ferrites. Now we will see how these ferrites are useful in refrigeration application. We have focused on zinc ferrite nanoparticle because it's known for their paramagnetic behavior. The nanoparticles have been synthesized through microwave assisted co-precipitation method. We have used a domestic microwave oven, and with this composition, just for 7 minutes, we did at 700 watt. Okay, the dried sample were investigated for various analysis. The structural analysis shows the synthesized nanoparticle has a single phase zinc ferrite with average crystallite size of 5 nanometer. The same has been confirmed with the TM analysis. The nanoparticle synthesized through this method is approximately of spherical in nature. Even the size distribution is very, very narrow. Okay. And to prove the Magneto-caloric effect, first we need to check the blocking temperature, where will be the transition temperature here. It shows zero field cool and field cool curve, you can see here. And where we have the transition, it about close to 25 Kelvin. To get the clear transition, you can do the derivative of magnetization versus temperature, will give you an exact transition temperature. Okay, and here we have arrived the blocking temperature approximately at 25 Kelvin for zinc ferrite nanoparticle, and there is a irreversibility temperature. The difference between the blocking temperature and irreversibility temperature will give an approximate an idea about the particle size distribution. If the difference is less, then the particle size distribution is very narrow. Okay. The narrow size distribution is really important for the case of magnetocaloric effect in nanoferrites. Okay. And here, to estimate the magnetic entropy change, we need to perform isothermal magnetization curves, which is nothing but we need to perform the MH curves at different field and temperature. Here we have started from 5 Kelvin to 305 Kelvin with a step of 10 Kelvin. Okay, we have performed this isothermal magnetization curve. Here we have observed there is a transition at 5 Kelvin, sorry, at 15 Kelvin. That's why the magnetization is higher at 15 Kelvin and then it come back to lower magnetization at 5 Kelvin, which is due to a spin disorder nature that we have also observed in FC curve here. And I showed you before the equation, Maxwell equation. By using Maxwell equation, we can estimate the magnetic entropy change of zinc ferrite nanoparticles. But we have extracted that data from the isothermal magnetization curve. We need this curve first to estimate the magnetic entropy change. What you see here, the magnetic entropy change increases with increase of field as well as the temperature. Okay, that's what you see here. At maximum field, let's say at 4 Tesla, here are 40 kilovolts, we can able to go up to minus 0.65 joule per kilogram Kelvin. There is a maximum magnetic entropy change that we have observed here. And we can also estimate the refrigerant capacity. It shows around 187 joule per kilogram at 40 kilovolts. Okay. We also worked with other spinel ferrites. Let's say the same synthesis method have been adopted to synthesize zinc copper ferrite, nickel zinc ferrite, zinc gadolinium ferrite as well. And they are approximately spherical in nature. And the size, you can see it varies from 5 to 7.5 nanometer, not more than that. So we could able to control a size if we use this microwave assisted co-precipitation method. And it is very, very rapid, or you can say quicker to complete the synthesis. And these nanoparticles also have been found with a magnetocaloric effect, but it has different behavior. In the case of zinc ferrite, we have seen already, but in the gadolinium doped zinc ferrite shows better magnetic entropy change in the cryogenic condition. But at higher temperature, it resembles the same behavior that we have observed in zinc ferrite. But nickel zinc ferrite, if you look at it, the magnetic entropy change increases, right? It increases and then it reaches the saturation, even close to room temperature. If you look at, if we have the material with this behavior, which has a table-like structure, it may go beyond 300 Kelvin also, right? So in this case, we believe that the refrigerant capacity of nickel zinc ferrite would be better than all other composites. The zinc copper ferrite composite also exhibit a magnetic entropy change. And here in all the cases, when the field is higher, the magnetic entropy is also higher. But we don't see any relevance between the blocking temperature and magnetic entropy change. Here, even if you have seen here, in the case of zinc ferrite, the blocking temperature is achieved around 25 Kelvin, but the maximum magnetic entropy change is observed around 150 Kelvin. Okay, we usually observe 4 to 5 times uh, um, at greater temperature than the blocking temperature, even in all other ferrites also. This is due to various factors like Zeeman energy. We need to consider the magnetocrystalline anisotropy energy, shape factor, right? Various anisotropy has to be considered to prove that. Okay, and here, as I told you, we have achieved appreciable magnetocaloric effect and refrigerant capacity in these superparamagnetic nanoferrites. The next one, I'll be focusing on graphene-ferrite nanocomposites for magnetic refrigeration. You know what is graphene, right? The most common allotropic form of carbon is known as graphite, which is available in the natural material, right? We say it's a natural mineral. It consists of sp2 hybridized carbon atomic layers, and which are stacked together by a van der Waals forces. But the van der Waals forces are very, very weak. If you look at it, the single layers of carbon atoms are tightly packed into a two-dimensional honeycomb crystal lattice known as graphene. Okay, and this name has been introduced in the year 1994. Why they are special? They are special because they low cost, highly stable materials, lightweight, and it exhibit excellent electrical chemical properties. See, in addition to these properties, it also has a magnetic property. It also has magnetic properties. The presence of defects, we say intrinsic, extrinsic defects, can induce different magnetic ordering in graphene nanostructures. The amount of defect density and the nature of defect in the graphene has a strong influence on the magnetic ordering of graphene nanostructures. And here, if you look at it, we have we can see through this paper, like the impurities can induce a defect. The single atom defects can also be the voids, and vacancies can be created by a foreign element. When we use a foreign element to create an defect, it can or it could give some magnetic ordering in the graphene nanostructures. Okay, we are going to see here this particular composite, graphene nickel zinc ferrite composites, and we will realize how this defect induces a magnetic defect. And here, this particular composition has been chosen because in this article, they have showed that nickel zinc ferrite exhibit a better magnetocaloric effect close to room temperature. And nickel zinc ferrite graphene composites have been synthesized through microwave assisted co-precipitation method of same parameter that we have used for zinc ferrite. But we have changed the graphene loading. Let's say from 20 to 100 milligram, we have changed the graphene loading during the synthesis of nickel zinc ferrite. Okay, during the synthesis, we have loaded it. We have not separately loaded. During the synthesis, we have loaded. And we see here through the structural analysis, the graphene has been found in all the compositions. In addition, the nickel zinc ferrite has been formed without any other phases. Okay? So we could able to achieve a single phase with this microwave assisted co-precipitation method. But when we loaded with 100 milligram of graphene, the graphene enhances the burst of nucleation rather than crystallite growth. That's why the crystallite size is not enhanced much greater than 7 nanometer. Okay, and here to prove the defect density, Raman spectra analysis should be done. Here you can see the two vibrations. One is at 1343 and another one is at 1586 per centimeter. Okay, and these two absorptions are correspond to D band and G band. The D band are due to a K point phonons of A1G symmetry, and this is due to a lattice defects and edge atoms. The G band is from a plane stretching vibrations of carbon sp2 atoms in 2D hexagonal lattice. Okay, now we need to check the defect density. What we do, we need to take the ratio of the intensity of ID by IG. If we take this, then this will give us defect density. In these 4 samples, here we have the plain nickel zinc ferrite and then graphene nickel zinc ferrite composites. Among these composites, the nickel zinc ferrite with 60 mg of loading has better defect density when compared to others. Okay, so here what do we see when we use nickel zinc ferrite, and this nickel zinc ferrite attachment to the graphene, they induces a side defect. Why? Because there will be a strong interaction between the ferrite nanoparticles and graphene nanostructures. Okay, now we have to confirm whether it shows a magnetocaloric effect or not. We have performed the isothermal magnetization curves from 5 Kelvin to 300 Kelvin. Then we have used Maxwell equation to estimate the magnetic entropy change. And here we have the nickel zinc ferrite. Even in other composite, also it has to show the similar behavior, right? But instead, in the case of composite, you see a different behavior. In addition to nickel zinc ferrite, now we have graphene with different defect density, right? Here, what you see, the magnetic entropy change that we have calculated with Maxwell equation. And here among these 3 composites, nickel zinc ferrite with 60 mg of loading shows better magnetic entropy change than other 2 samples. Okay, now here you see some anomaly, right, at nearly 56 or 57 Kelvin, and here around 40 or something, and here it's around 250 Kelvin. You have seen some anomaly, and these anomaly are due to defect present in the graphene nanostructures. Okay, and here if you look at this defect, the defect induced magnetocaloric effect is superior than the nickel zinc ferrite. That you can see from this diagram. Wherever the defect density is more, the magnetic entropy change is also high. Okay. Now, we do not know what would be the reason for this transition. And to prove that, we need to perform the magnetic susceptibility versus temperature analysis. And here, the nickel zinc ferrite, you can see this nearly up 50 Kelvin, it shows the blocking temperature. At blocking temperature, what happens? It will transform from ferro to paramagnetic. In the case of N is of G2, it has 2 transitions. One is at antiferromagnetic transition, nearly at blocking temperature, and then ferrimagnetic transition up to 150 Kelvin later, it transforms into a paramagnetic. That's why you see here one transition, and then later you have another transition because there is a ferrimagnetic transition and then ferrimagnetic to paramagnetic. In the case of NZ of G6, we observe a ferrimagnetic transition at low temperature, and then antiferromagnetic transition has been observed at later a ferro to para transition. Antiferromagnetic to para transition is observed close to a blocking temperature. But the last composition is very similar to a nickel zinc ferrite at low temperature region, but at 250 Kelvin, it shows a transition from ferrimagnetic to a paramagnetic. Okay, and what about the magnetic entropy changes as well as refrigerant capacity? We have estimated in addition to magnetic entropy change, refrigerant capacity has also been estimated, which shows that 217, 143, 155, and 105 joule per kilogram for these composites respectively. But what about the delta T? The delta T is much higher than the nickel zinc rate that we have achieved. And to summarize the part 2 of my talk, we have synthesized the different ferrite nanocomposites and as well as ferrite, which exhibited better magnetocaloric effect, but especially in the case of nickel zinc ferrite graphene nanocomposites, if we can increase the defect density in graphene nanostructure, the magnetic entropy change can also be enhanced. Among various ferrite nanocomposites, we have compared our results. Among different spinel ferrite and ferrite nanocomposites, the results that we have achieved from our group shows better magnetic entropy change in the especially magnetic entropy change, but the refrigerant capacity is comparable to the literature value. The last one I would like to stress here on refrigeration from the crystals. Here we mainly focus on manganese phosphorus crystals because they exhibit orthorhombic structure at room temperature, as well as there will be a transition from ferromagnetic to paramagnetic close to room temperature. And here they exhibit this transition ferro to para at room temperature. In addition, we'll be having a screw and fan transitions at different temperature in the cryogenic region. Okay. And we know the dimensionality effect, right? When the size of the material reduced from bulk to nano, but the composition remains the same. When we compare the properties of the bulk and nanostructures, the nanostructure material gives a better property than the bulk materials. The reason is a large surface to volume ratio compared to the bulk materials. Okay. Here we are intended to study the dimensionality effect on the MNP, manganese phosphorus crystals. Okay, so what will happen here? This is a bulk nanostructure. Let's say the magnetic entropy change is higher, but the working temperature, if you look at it, is very nano. If you reduce the size of the same composition, we expect that we could maintain the magnetic entropy change and increase the working temperature. This is an idea. So how can we do? We use a magnetic flux nanonucleation method to achieve manganese phosphorus single crystal as well as one-dimensional nanowire. The fused quartz strip has been taken, whereas we kept anodized alumina template at the bottom, and then manganese phosphorus tin as a flex has been considered. Okay, there will be a quartz bull has been put it inside this alumina crystal. This is the temperature profile we have chosen. It starts from room temperature to 1150 degrees Celsius. We maintain at this temperature for 6 hours. To achieve very good quality crystals, we need to do a very low rate cooling performance. Okay, so you look at it here, it has taken 200 hours to reach this 100 degrees Celsius. After that, it has to be removed out suddenly, and then we have to centrifuge to get good quality crystals without any flux. And these are the crystals we have achieved. We have varied the flux concentration. Let's say 1:1:10 and 1:1:20 percentages of manganese phosphorus tin has been taken. Okay, and here if you look at it, we have achieved manganese phosphorus of nearly of 74% with and secondary phase of Mn2P of 21%. In addition, a small amount of flux has also been found, and it exhibited orthorhombic structure as we have showed you in the beginning of the slide. Okay, and how it has formed, how the nanowires are there inside the alumina template. It can look at this alumina template that we have used for the nanostructure fabrication. It has the mean core diameter of 124 nanometer. This is the mean core diameter. Okay, and here you can see the MNP nanocrystals are infiltrated through this alumina template, and you can see very clearly here. But we need to break this template to see a single nanowires. And in other composition, let's say in 1:1:10, it forms a nanogranules. It forms a nanogranules over the alumina template. Okay. And we have performed the magnetic properties, magnetic analysis on these crystals, bulk as well as nanocrystals. And here you can clearly see the transition, ferromagnetic to paramagnetic transition at room temperature as well as screw transition at low temperature. Okay, and we have chosen different crystals to see the uniformity, to check the uniformity of the samples. And here with the same composition, we have chosen crystal 1 and 2. It has some different magnetization behavior because it has an anisotropic effect. If we change the direction of magnetization and towards the magnetic field, it exhibits different magnetization behavior like this. Here in the case of sample 1, you can see it magnetizes quickly, but in the other case, it needs more magnetic field to reach the magnetization value. Okay. And to prove the magnetocaloric effect, we need to perform isothermal magnetic entropy, isothermal magnetization curves. And with that, we can estimate the magnetic entropy change. Here in bulk crystals, it shows better magnetic entropy change close to room temperature. We have achieved a refrigerant capacity of 147 joule per kilogram in the crystal 1. In the crystal 2, we could able to reach of about 171 joule per kilogram Kelvin. Okay, and how it behaves in the case of nanowires. In the case of nanowires also, we see the transition, ferromagnetic to paramagnetic transition, as well as screw, ferromagnetic to screw transition have been observed. But the magnetization is very, very weak when compared to the bulk crystals. It exhibits paramagnetic nature. These isothermal magnetization curves used to estimate the magnetic entropy change. You see here, the magnetic entropy change is observed in these two crystals, especially nanowire crystals. But when we compare the magnetic entropy change, is the value is only 1% of the bulk crystals. Okay, fine. So to summarize that, we have synthesized a single crystals of MNP through metallic flux nanonucleation method. The beauty of metallic flux nanonucleation method is we can achieve a bulk crystal as well as nanocrystals of the same composition, right? We could do that, bulk as well as nanostructures. And when we compare these bulk and nanostructures, the bulk crystals exhibit better magnetic entropy change than the nanostructures, right? Of different compositions we have seen, isn't it? So what we have to do, we need to increase the magnetic moment of the sample. If we could increase the magnetic moment, or else we say if we increase the magnetization value of the nanowires, then the magnetic entropy change would also increase. Okay. To summarize overall, in the first part, we have checked multiferrite nanocomposites. Right, these nanocomposites have been synthesized through solution casting method. And we have also proved that the magnetoelectric effect depends on various factors. One is ferrite type, ferrite content, and the fraction of beta phase in the composite. In the case of magnetic refrigeration, the beta behavior has been observed where the magnetic moment is higher, or we say where the magnetization is greater. It depends on the factors like particle size, composition, as well as defect density in the case of graphene and nickel zinc nanocomposites. Okay. Finally, the single crystals have also been discussed. Okay. I must acknowledge my supervisors, who is the pillar of support for these studies, and financial support from the agencies. One is from faculty and funded postdoctoral fellowship to perform this analysis. And I take this opportunity to introduce the PhD program available in our university. We offer a PhD program. in our university of different research areas. Okay, you can do full-time research position here of 3 years, and this is fully funded, and you need to pay the tuition fee of nearly 40,000. You can check it here. And then what you will get? You will get a fellowship of 31,000 in the second year onwards. But in the first year, you will get 25,000 if you are not qualified GATE. But if you qualified JRF and GATE, you will get 31 in the first year and 35 from the second years. But this fellowship is only for 3 years, and you have to plan very well to complete the PhD within 3 years. If it goes beyond 3 years, then you cannot complete it. And at last, I would like to also emphasize that we offer MSc programs in general physics as well as energy technology. And if you do with this, there will be a chance to proceed PhD. Okay, there is a chance to proceed PhD at VIT University. And if you have secured higher percentages, let's say 90% in your undergraduate program, then this will be completely free. You are going to perform your graduation on a free of cost. Okay. With this, thank you everyone for listening to me. Now, I can answer if you have any doubts.
Dear participants, now it's time to queries. Have you any queries? Okay, sir, no more queries. Now, I would like to give a vote of thanks. On behalf of HNBA's department, today I take this opportunity to put all my gratitude in the form of words. First of all, I would like to thank our today's eminent speaker, Dr. Prabhakaran Garu, for accepting our request and for giving such a wonderful presentation on magnetic materials and composites for different applications and making event meaningful and interesting. Thank you very much, sir. And I would like to express our profound gratitude to our principal, Dr. Syed Suraya ma'am, for her constant support and encouraging throughout the program. Thank you so much, ma'am. Now, I would like to extend my heartfelt thanks to entire management, correspondent madam, Srimati V.K. Padmavatama Garu, for her encouraging words from the beginning of the session. Now, I would like to thank our director, Srimati V.K. Vani ma'am, who has initiated to do us this program and her continuous support right from its inception. Thank you so much, ma'am. Now, I would like to express my gratitude to our managing director, Sri Raghunath Reddy sir. Thank you so much, sir, for your supporting us and guiding us in the right way, sir. Thank you so much, sir. My heartfelt thanks to our convener, Dr. G. Haripriya ma'am, and her entire team, co-convener, Mr. Shivaya sir, and Dr. Jansi Rani ma'am, Mr. Jayaprakash sir, Mrs. Suman Gopinath ma'am, and Angeline ma'am for their continuous support in making second day of this FDP successful. A big thanks to Noor sir and Nagendra sir, who is the backbone of this online session by providing technical support. Thank you so much, sir. Finally, at the end of the session, I would like to thank all the participants of this FDP for their glorious presence. Thank you. Thank you so much for each one of you.
Thank you. Thank you very much for giving me an opportunity to
Thank you,
share
sir.
some of my research works with the audience.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, Dr. Sivaya sir.
Okay,
Okay.
thank you, sir.
Thank you, sir.